All right, so this final video is going to focus on colligative properties. This is just an application of solutions, and it basically is used to describe how the number of solute particles can have an impact on various properties of an ideal solution. It doesn't matter the identity of these properties or particles, just the number of them that are present in your solution. They can have an impact on the vapor pressure by lowering it, on the boiling point by elevating it, and on the freezing point by depressing it. So we're going to start by talking about vapor pressure, and Raoult's law is used to describe how a non-volatile solute, a solute that is not exerting pressure, is going to lower the vapor pressure of your solvent. Your solvent, being a pure solvent, has its pressure, but when you have a non-volatile solute present, it interferes with the solvent's particles' ability to exert pressure on the surface and to be able to escape and become a gas. And so the vapor pressure of your solution will actually be lowered, and it is dependent on the number of those solute particles that are present, the fraction of the solvent that is still in the solution. The more that's there, the greater that pressure of the solution will be, and the closer it will be to the pressure of the pure solvent. So here's kind of a visual to see what the difference is. There's your pure solvent just running around colliding with one another. And so there's nothing interfering with its ability to reach the surface. So it has that pressure gauge marked over to 3. And then you have the non-volatile solute with the yellow particles that are interfering with that process, and that goes to 2. So the non-volatile solute just basically makes it more difficult. It uses up some of the energy that the green molecules would use to reach the surface by colliding with them, and that's going to reduce the overall pressure. So here we have a solution of ethanol. There's 53.6 grams of glycerin and 133.7 grams of ethanol. It's at 113 torr at 40 degrees Celsius. We want to know what the vapor pressure is of pure ethanol at 40 degrees Celsius, given that glycerin does not exert any pressure on this solution. It is a non-volatile, it's a non-electrolyte, so it doesn't separate into ions in the presence of ethanol. So as you saw in that previous equation, to calculate pressures using Raoult's law, we need to have mole fractions. We want to have a mole fraction specifically of our solvent. So we have the grams of glycerin and we have the grams of ethanol. And we're going to convert those both to moles using our molar mass. So 53.6, when it's converted, is going to give us 0.582 moles of glycerin. I would just take the molar mass of glycerin and divide it into that 53.6. While the 133.7 grams of ethanol, when it gets converted using its molar mass, is going to have 2.901 moles. The mole fraction of the solvent is what we are looking for, so I need to put the moles of the ethanol. It's always the one with the larger quantity that's acting as your solvent. I need to put that in the numerator and divide it by the moles of both the solute and the solvent. And once I get that value, I have the mole fraction of my solvent. So 0.8329 of this mixture, of this solution, is made by moles of my solvent. You were given the pressure of your solution. You were told the pressure of your solution was 113 torr. So the pressure of your solvent should be greater than that, since that 113 torr is lowered due to the presence of this non-volatile, non-electrolyte solute, glycerin. So when I do my math through and I solve for the pure vapor pressure of my solvent, I get that the actual pressure was 136 torr. With boiling points and with freezing points, adding a non-volatile solute interferes with the ability of that solute to be able to escape and reach the surface, and so it takes more energy to get those molecules to reach have the same vapor pressure in the liquid as they do in the atmosphere surrounding it. And so that would cause your boiling point to be higher. And we can calculate what that temperature change is by taking the molal boiling point elevation constant and multiplying it by the molality of our solution. We use molality because molality is independent of temperature, and that's what we're trying to find out about, is how do these particle amounts influence the temperature that this substance will boil at. So with freezing point, it's going to interfere with that freezing process, and it actually causes the freezing point to become lessened. It takes more energy to get all of the solute to kind of separate so that you can get your solvent to completely freeze again. And so that too is based on molality, and this is really critical in terms of determining the composition of the salt mixture that is put on our roads in the wintertime to make it safe for us to drive when the temperature drops. In all three of these scenarios, the number of particles is going to influence these very properties: your melting point, your boiling point, or sorry, your freezing point, your boiling point, and your vapor pressure. I is known as the Van Hoff factor, and it's basically telling us how many ions are available based on our strong electrolytes. If you don't have a strong electrolyte, your I would be 1. But NaCl would produce 2 ions in solution. It would produce a sodium ion and a chloride ion, so it would have an I value of 2. Potassium sulfate, sulfate would be one of the ions, potassium would be the other. You have 2 potassium ions present, so you would have a total of 3 ions in a solution of potassium sulfate. So when we are calculating our properties with this Van Hoff factor in mind, we include that value for its I. So here I have 4 different substances. One's pure substance, the rest are solutions. I have pure water, I have sucrose in water, salt in water, and calcium chloride in water. The sucrose, the NaCl, and the calcium chloride all have the same molality. So with that in mind, I want to know which of these would have the highest freezing point. Which of these would freeze the quickest? And the one that would freeze the quickest would be the one that is just the pure solvent, water, because it doesn't have anything interfering with its ability to coalesce along amongst itself and to form its crystalline structure. The one with the lowest freezing point, they all would have the same constant K because they're all the same solvent. They all have the same molality. So the one that's going to have the lowest freezing point is going to be the one with the greatest I value, because that's going to cause the greatest change in your temperature. So the two that are capable of producing I values other than 1 are NaCl, which would have an I of 2, and calcium chloride, which would have an I of 3. So calcium chloride would have the lowest freezing point. Which of these would have the highest boiling point? It would be the same as the one with the lowest freezing point, because boiling point is elevated by the number of fat ions that are present. So that would be calcium chloride. And the one that would have the boiling point that is the lowest would be the pure solvent, and that would be water. Here I'm asking you to calculate the freezing point of solution A and the boiling point of solution B. So the freezing point of solution A is given to us as being 0.250 molal AlBr3. So if we use our equation for freezing point, delta T equals I times Kf times M, we know that for AlBr3, there's aluminum and bromide, and there are 3 bromide ions present. So we would have an I of 4. You were given the Kf value, that it changes 1.86 degrees Celsius per molal. This is specific for water. Every solvent has a unique Kf, and you were given the molality, 0.250. So if I substitute in those quantities, I should be able to calculate what the temperature change is for this solution, and it was 1.86. Now, keep in mind this temperature change is the difference between the pure solvent and the solution, and so the pure solvent would have a freezing point of 0. And because freezing point drops, that means that the new temperature would be negative 1.86 degrees Celsius. For the boiling one that we're going to look at next with Ki, we're still going to be using that same delta T equation, but we're going to use the Kb for water, 0.52, Ki only has 2 ions that are able to form in solution, one potassium and one iodide. So we're going to substitute those 2 quantities in along with its molality. And when we do our math through, we get that the temperature change was 0.13. Now, water would normally boil at 100 degrees. So if water normally boils at 100 degrees and the boiling point goes up, it would go to 100.13 degrees Celsius. The last question we're going to take a look at is just kind of an application as to how we could use these colligative properties to find out about another characteristic about one of our components. Here we have a solution that consists of 21.3 grams of a non-volatile, non-dissociating solute that's found in 250 grams of benzene. So we're going to have a different Kb value because we're dealing with a different solvent. This time it's benzene. It freezes at 83.4 degrees Celsius. The normal boiling point of benzene is 80.1, and we want to know what the molar mass is of our solute. Well, molar mass is grams per mole. And we have the grams of our solute. We have the grams of it being 21.3. So we need to find the moles of our solute. Well, we don't have anything offhand that's going to help us find moles of solute since we don't know its identity, but we do have the ability to use colligative properties to find out information. And specifically, we can find out from the information that's given in this problem the molality of our solution. We have the 2 temperatures, the temperatures at which, I don't know why I have that it freezes at 83.4. Super sorry about that. It boils at 83.4. I will fix that for my presentation. And that the normal boiling point is 80.1, so we can calculate what the temperature change would be for boiling, 3.3. This is a non-dissociating solute, so the I value would be 1. We have the Kb for benzene being 2.53, and we can use those pieces of information to find the molality of our solution, which contains the moles of our solute. So we know now that there's 1.3 moles of this solute per 1 kilogram of benzene. Well, we did not dissolve our 21.3 grams in 1 kilogram of benzene. We dissolved it in 250 grams. So if we use our molality to solve for the moles of our solute, 1.3 moles per kilogram, again, is our molality. We have 0.250 kilograms of solvent. We do our math, we get 0.325 moles of solvent, 0.325 moles of solute. And now that we have the 21.3 grams of our solute, when we divide those two, we can get our molar mass, 65.5 grams per mole.